Hello, my name is Ho-Jun Lee, and I'm an undergraduate student in EE department. And I'm going to introduce this paper, Surface Code towards Practical Large-Scale Quantum Computation. And Surface Code is one of a quantum error correcting code. And first, let's see why quantum error correction is needed. Because quantum computers are extremely susceptible to noise, and many noisy quantum operation can result in fatal errors. So, and we can reduce error by quantum error correction by adding redundancy. First, let me introduce the simplest code, the bit flip code. We encode 000 as logical 0 state and 111 as logical 1 state. And this is the encoding circuit. Bit flip code can detect a single Pauli X errors. And if we use two CNOT like this, and these first and second qubit are different, the ancilla becomes 1, and we detect the error. Let's define a syndrome measurement. S1 is a measurement result for first and second qubit, like previous circuit. And S2 is measurement result for second and third qubit. If S1 equals 0 and S2 is equal 1, it means only third qubit is different. So Pauli X error occurred on third qubit, and we can correct by applying Pauli X at third qubit. And this table informs how to correct the error for each syndrome measurement results. But what if a Pauli X error occurs on both first qubit and second qubit? And it also has measurement result 0 and 1. And this bit flip code cannot protect this error. And it occurs a logical error. And let's consider this model. For each qubit, Pauli X error occurs with a probability P, and there's no error with probability this, and 1 error, and 2 errors and 3 error with probability this. And we can only correct until 1 error. So we can reduce the error rate with using this code when P is less than half, 1.5. And there is a nice formalism that can represent quantum error correcting code. We can represent the code space with G's that stabilize every state in the code space. And for example, the bit flip code is stabilized by these stabilizers, and this one is the generator. You can see that these logical 0 state are stabilized by all of these stabilizers, and logical 1 is also stabilized. Before I introduce the surface code, let me introduce 5-qubit perfect quantum error correcting code. The perfect quantum code is stabilized by these 4 stabilizers, and we can encode the code like this. This I plus G term means that is stabilized by GI, because we multiply GI and it gives I plus GI. And we can detect error by measuring stabilizers. Since it's a stabilizer, the measurement result, the eigenvalue must be 1, and if the eigenvalue is -1, the error occurred at this stabilizer. And perfect quantum code is a minimal non-degenerate quantum code, which means we can perfectly know what error occurred on which qubit. And someone can think quantum error correcting code could only correct Pauli errors, but it's not. Let's say an arbitrary error occurred on logical qubit, and we can represent the error like this. EI is a tensor product of Pauli errors. And in error correcting process, we prepare an initialized ancilla, and we entangle qubits with ancilla to for the cylinder measurement. We can represent that like this. And after the cylinder measurement, it becomes one of the SIs, and we can correct the error by applying EI. Now, I'll introduce the surface code. The surface code consists of 2D square minus 2D plus 1 data qubits, which are white one, and 2D square minus 2D major qubits, which are black one. And they will be used for the syndrome measurement. For these 4 data qubit, we measure Pauli XXXX like this. And this is called measure X qubit. And for these 4 data qubits, we measure Pauli ZZZZ, and they are stabilized by ZZZZ operator. And we call the state that are stabilized by all measurement qubits called quiescent state. And they have 2 times 2D square minus 2D plus 1 degrees of freedom, because it has these data qubits, and they are 2 times 2D square minus 2D constraints. So the quiescent state has a 2 degrees of freedom, and we can use this as a qubit state. And let's consider some error cases. If X error occurs this qubit A, and then the stabilizer GA, GB, GC, GD anti-commits with XA, so the stabilizer detects this X error. And also this GGG major qubit detects the error. And if G error occurs, the adjacent major X qubit detects the error. And if Y error occurs, adjacent major X qubit and major Z qubit detects the error. Since quiescent state is a qubit state, we can define logical X and Z operators. And these operators should commute with all of the stabilizers. We define a logical X operator like horizontal line of X and ZL as vertical line of Z operators. You can wonder, and these logical X and Z operator anti-commits. So it can play a role as a logical X and Z. And you can wonder the other choice of logical operators. Let's define another logical X operator, XL prime, like this one. And XL prime is a product of XL and this square. So since this square is a stabilizer, it has eigenvalue 1. So the XL prime and XL is equivalent for the quiescent state. Then what is the logical error rate? Let's consider this error model. And roughly it means an error occurs with a probability P for each step of error correcting process. And logical error rate PL is like this. If the error probability P is less than this threshold, the logical error rate decreases by increasing the distance of the surface code. And this is the graph for the logical error rate. You can see it decreases by increasing distance. For example, this distance is 3, and distance 3 means product of Pauli product of 3 Pauli errors, then the logical state changes 0 to 1. So it can correct only one errors because it has distance 3.
So having distance?
It's similar one. But just error is Pauli error. And surface code has only two X and Z boundaries, so it only gives a single logical qubit. And by increasing the number of, we can increase the number of logical qubits by creating more varied boundaries. And one of the method is creating a hole. We can create a hole by turning off the Z stabilizer, and it gives 2 additional degrees of freedom. And we can define new logical operators like XL and ZL. You can see these anti-commits each other and commit with original X and Z operator and commit with stabilizers. One disadvantage of the single Z-cut qubit is that the hole relies on the boundary. With this double Z-cut qubit, we can create a logical qubit that is independent to the boundaries. By using ZL1 and XL as a logical operator, we can make the hole independent to the boundary. And distance of this code is minimum of 4 and the length of XL, but we can increase the hole. We can increase the distance by enlarging holes like this.
So if we make a bigger hole, then we get the degree of freedom. So how many holes do we need to get 1 degree of freedom? Am I understand?
By turning off the stabilizer, and one constraint disappear. So 2 degree of freedom created. In this case, there's 4 additional degrees of freedom, but we only use 2 of these. To implement the C0 operator, we have to move qubits. And this is the process of moving Z-code logical qubit. First, turn off these Z stabilizer and make this X stabilizer from 4 terminals to 3 terminals. And measure X6 with the X basis and turn on the original measure Z qubit and convert back the measure X qubit from 3 terminal to 4 terminal. Then we can define new logical operators XL prime and ZL prime. And ZL prime is equivalent as this one. And it can have minus sign from the measurement result, but we don't have to worry about these signs because the signs are monitored by software control system and instead of correcting immediately. And these moving qubits can be extended to multi-cell loop by creating
What does it mean to turn off and turn on terminal?
Turning off means we don't stabilize that qubit next cycle. Cycle means stabilizing process. We operate some operation and stabilize to the code space.
Okay. I think
And we can implement CNOT by braiding the qubits. There is a one Z-code qubit and X-code qubit, and there is a logical X operator. By moving this qubit through the X-code qubit, it becomes XL1 product XL2. So the braiding transformation transforms X1 to XL1 to XL1 XL2. For the operation A, if it follows this one for any Pauli operators, we can say A and C are equivalent. And proving about these ones are equivalent enough because we can make any of these by producting these ones. And C0 transforms Xi to XX. And also the braiding transformation transforms Xi to XX. And it transforms IX to IX and GI to GI and IZ to ZZ. And for IX, braiding process does not do anything. So IX becomes IX by braiding. And IZ becomes ZZ. And Ci also do nothing. So we can say that grading transform is a CNR operation on the surface code. And next is the Hadamard operator. And the following process is applying Hadamard on this dashed patch. And if X becomes Z and Z becomes X, we can say that this transformation is a Hadamard transformation. But I will skip this because it's too complicated. And we can implement the S operator if we have this logical Y state by operating like this. But then how can we prepare Y logical Y? We can prepare a logical Y state like this process. First, turn off the two X stabilizers and measure this qubit with basis X. And it is sort of logical X, but it's just a dot. So it creates logical plus and minus. And we rotate this qubit physically. So with that z-axis with phi over 2, and it makes we can make logical Y. But this is necessarily imprecise because we did physical rotation. Usual method, just one qubit.
We can say, I think it means choose the face. And the face choose can be what you say.
Yes. Since this is imprecise, we have to make precise. And we can make more precise logical Y with 7 imprecise Y's with this state distillation. If logical error rate for the original Y state is P, then the logical error rate for the distilled Y state becomes 7P to the 3. And the success probability of this process is 1 minus 7P. And this process is based on 713 Steam code. And we can also implement T operator like similarly. So we implemented X, Pauli, X and Z, and C naught, and Hadamard, ST, so we can do quantum computing with the surface code. Conclusion is the surface code has high per step errors ratio, about 1%, but and Steam code and Bacon Shore code has 2 times 10 to the minus 5. But the surface code requires a very large number of physical qubits. We need thousands or 10,000, about 10,000 physical qubits for one logical qubit. And in order to achieve logical error rate like below this, and we needed order of 10 to the 8 for practical factoring. And thank you for listening.
Any question?
I understand. So we only can have just like pepper, or we can have another.
There is another pattern, but it's basically chess pattern.
Ah, why should it be like that?
Uh, because it G and X uh,
Not together?
in this pattern G and X always commutes because it has two data cubic.
Commutes. So
They commute so they can be stabilized by both stabilizers.
um, black one is for the that
For the measurement,
what is the difference between black and
white one is extra qubit, extra
X stabilizer and
white one is a data qubit that we use in the computation, and the black one is for measurement.
ah. So we only measure the black.
Yes.
And X1 is
X is just a letter. It means
X. Okay.
this one measures X axis on
The
this.
height one does not measure. Yeah. Then what does it do? It just means I need to measure here. Okay.
It means the state, like actual state is the white one.
Extra thing.
Actual state is
Ah. Then it's not. Okay.
So in summary, if we measure black, then get another minus when we apply stability answer, especially plus one, two.
this decoding process is quite complicated. So there is another algorithm for decoding. We detect the syndrome measurement, and there will be some minus ones. And by decoding algorithm, we can determine where the error occurred.
And so by measuring one qubit, we know where the error occurred on the qubit. The second question,
Can you say it again?
검은 거 하나
네.
정해서 그 주위에 있는 네개 중에 어디에서 내가 발생인지 알 수 있다.
바로 하나만 있을 때는 알 수 있는데 보통 여러 개 생기면은 그 가장 에러가 많이 발생할 것 같은 그 확률이 높은 그 조합을 거기서 에러가 발생했다고 하잖아요. 네.
일단 다 측정하는데 그다음에 어디서 에러 발생했구나 이 확률이 제일 높은 결정가 따랐다. And so I have another question. So is that we need 10 to the 8 powers of qubits per chemical qubits? We need 10 to the 8 powers of qubits.
10 to the 3 or 4.
Right, for factor entering
A.
series.
That is the minimal one.
So, how do we connect all the state, like if you're using totals that is still very hard, but it can be achievable, I think. But like if you're using non-conducting qubit state, it's going to be very challenging.
I heard that using superconducting quantum computer is best one
For this.
for this surface code. So Google have an experiment for 5 distance surface code.
So how many qubits?
Maybe 49 with 72 sycamore computer, and the pattern is a little bit different with this one.
It's still very far from 1,000 qubits or 7,000 qubits.
And I think there is something like three-dimensional surface code. Do you know about that? Like some advantage of having a three-dimensional surface code.
I have read the 3-dimensional surface code, but I can't find any advantage. Maybe I don't know about it.
I think in case you know, like I just heard about it, and I was wondering what it was like.
So this only works for Pauli operations. In the system using Pauli operations and existing operations.
Yes.
And what is the computational overhead like in terms of time complexity to correct one using surface code?
Operating hardware has much overhead,
Okay.
and we need to also have a stabilizing cycle.
Right. So I guess it's in terms of time complexity, quite expensive.
Mm.
But it's also constant vector, very large constant vector. So that can be customized.
Mm.
So I think the overhead is very large, but depends on number of qubits. So it's constant.
I don't know, but it's not too much large. This overhead is not too much, but
Any other questions? And so thank you, Professor, for the presentation. Okay, so thank you for